Good morning to all. So today we will be discussing the terminologies in the mechanical properties of material in the course Material Science PH8251. Stress. What is stress? Stress is force per unit area. It can be either tensile stress or compressive stress in case of normal stresses, or it can be tangential stress, that is shear stress, where the force acts in a direction tangential to the area under consideration as seen here. So stresses can be either normal stress, further classified as tensile or compressive, or shear stress. Okay. Strain. Strain is change in dimension per unit length. In mechanical properties, we will be usually dealing with a material subjected to a tensile test. So, here it is usually increase in length by the original length. Since strain is a ratio, it has no dimensions. So, beyond the elastic limit, there is a residual strain after removal of forces. So, we need to know what is elastic limit, and this residual strain is called as permanent set or plastic deformation. So, we need to know what these terms means. So, we proceed to the stress strain plot. So, the stress versus strain plot is as seen for any material in general. And we have come across the stress strain plot while discussing about the properties of material, especially elasticity, in your first semester. So, initially, when a deforming force is applied, the tensile test specimen shows an increase in length, and when the deforming forces are removed, the material regains its original shape. This happens up to a particular point called as the elastic limit. Hooke's law is said to be obeyed in the elastic limit. That is, within the elastic limit, stress is proportional to strain. This is true only in the linear portion of the curve, and the slope of this linear portion is given the name Young's modulus E. That is the slope of the stress strain plot in the linear region. But beyond the elastic limit, the material enters the plastic region, and suppose a deforming force, say up to this point, is applied and the deforming force is removed, the material does not regain its original shape. Instead, it retraces a path parallel to the original path, and this residual strain which remains after removal of deforming forces is called as permanent set. The stress corresponding to the elastic limit is called as the yield strength. The stress corresponding to the maximum load the material can withstand is called as ultimate tensile strength or ultimate strength. Beyond ultimate strength, necking occurs and eventually the material fractures. Okay. So, now we will deal one common term used while discussing the mechanical properties of material. It is the strength. When we say strength, it may be either the yield strength or the ultimate tensile strength. We have explained what is yield strength and what is ultimate tensile strength. Yield strength is denoted by sigma y and ultimate tensile strength is denoted by sigma UTS. Strength in general is the ability to resist plastic deformation. The next important term while dealing with mechanical properties of materials is stiffness. When I say stiffness, the stiffness of the material is ability to resist elastic deformation. Note that ability to resist plastic deformation is strength, whereas ability to resist elastic deformation is stiffness, and it is quantified by the Young's modulus of the material. Toughness is the total area under the stress strain plot. That is, it is the energy absorbed per unit area of the material up to fracture. The typical engineering stress strain behavior up to fracture for a tensile specimen is described using this diagram. So, within the elastic limit, material undergoes elastic deformation and it regains its original shape after removal of the deforming force. Once it enters the plastic region, even after the removal of deforming force, there is a permanent set. That is the residual strain that remains even after the forces are made zero is called as permanent set. Once the stress level exceeds the ultimate tensile strength, that is the point M in this graph, necking begins, and you can see necking is narrowing down of certain regions of the specimen, and this necking continues till fracture. F is the fracture point. For a brittle material, there is no necking. The ultimate tensile strength corresponds to the fracture point. That is, the material breaks once the maximum load it can withstand is reached. Whereas for a ductile material, it has a very large plastic range. Ductility is elongation strain at fracture. It is the ability to undergo plastic deformation. Gold, for example, is the most ductile material. So these graphs shows the yield strength of few specimens of steel. This graph A, represents that of a mild steel, and note that the yield strength corresponds to a 0.002 offset, strain offset from the elastic limit. This is because of the fact that usually plasticity onsets after 0.005 strain. Okay, so that's why usually the yield strength corresponds to the value 0.002 of strain offset from the elastic limit. And here you have the stress strain graph for many steels where you have an upper yield point and a lower yield point. This is exhibited by many forms of steels. Next, what is engineering stress? Engineering stress is instantaneous force by initial cross-sectional area, that is F by A naught. And engineering strain is change in length by original length, that is L naught. L by L naught minus 1 or delta L by L naught. Whereas true stress is the ratio of instantaneous force by instantaneous area. Note that as the specimen is elongated, its area decreases because the entire volume of the material should remain a constant. Okay. So true strain is the natural logarithm of the ratio of instantaneous length to original length, that is ln of Li by L naught. So these plots shows the true stress strain graph versus the engineering stress strain graph. Note that the true stress strain graph is actually shifted upward as considered to the engineering stress strain graph, and the ultimate tensile strength is shifted to the left a bit, and usually it is truncated at this point. The relation between true stress and true strain. It is given by K sigma T equal to K epsilon T power n, where K is the strength coefficient and n is the work hardening exponent. Large work hardening exponent means large plastic strain. Example, copper and brass has a n value of nearly 0.5. If a material has a low work hardening exponent, example n is 0.15 in case of heat treated steel. So, relation between engineering stress and true stress. As I told earlier, the volume of a material is an invariant. So, A0 L0 should be equal to AI Li. That is, area times the length is a constant for at any instant. So, A0 L0, the initial area of cross section into length, should be equal to AI Li. Sigma T, that is the true stress, is F by AI, force by instantaneous area of cross section. So, using the expression above, it can be written like this, which mathematically reduces to sigma T equal to engineering stress times 1 plus engineering strain. Similarly, you can also prove that relation between true strain and engineering strain is given by epsilon T equal to ln of 1 plus epsilon. So, I hope that the terminologies explained so far is clear to you. Please read through the study materials provided for better understanding. Thank you.